The flat plate laminar boundary layer functions that were developed by Blasius can be used to find a number of different characteristics of a boundary layer. In this screencast, I'll show you how we use this table to find the boundary layer thickness at any point along a flat plate and demonstrate it with an example. By definition, the thickness of the boundary layer, which we call del, is the value of y where the velocity in the boundary u is 99% or 0.99 of the free stream velocity. In other words, u divided by u infinity equals 0.99. So let's look at this table here. And if you notice, between these two numbers is 0.99, which means that our eta is going to equal 5.0. That means that 5.0, if we look at what this column means, equals del, because that's where our y is, times the square root of our free stream velocity divided by the kinematic viscosity of the fluid times x, where x is the length along the plate. Let's write this in terms of del. So we're going to multiply the top and bottom of this by x. So we get that del equals 5.0 times x divided by the square root of u infinity times x squared divided by our kinematic viscosity times x, or we can write this as 5 times x divided by the square root of u infinity x divided by the kinematic viscosity. And hopefully we recognize this quantity in the denominator under the square root as the Reynolds number. That means at any x, if we know the fluid property, in particular the kinematic viscosity and the free stream velocity, we can find the boundary layer thickness, or del. Let's look at an example. Let's say we have water. It's at 300 Kelvin, and our free stream velocity is 2 meters per second. And what we want to do is find the boundary layer thickness at different points along the place. So the first thing that we're going to need is the kinematic viscosity of water at 300 Kelvin, and that's equal to 8.6 times 10 to the minus 4th meters squared per second. Next, we find the Reynolds number, which is defined as the free stream velocity times x divided by our kinematic viscosity. Our Reynolds number in terms of x equals 2,326 verse meters times x. So then when we put that into our equation that we found up here for del, we end up with del, which equals 5.0 times x divided by the square root of the Reynolds number, or 2,326 square root of x, and this equals 0.104 x to the 1/2. Let's look at this at different points on the plate. So let's say we look at 10 millimeters down our flat plate. Our boundary layer thickness is going to be 0.0104 meters. We look at 100 millimeters, and our boundary layer is 0.033 meters. And as we expect, as we go down further on the plate, our boundary layer thickness is going to increase. And in fact, at 1 meters, our boundary layer thickness is 0.104 meters. In fact, if we look at a plot of the boundary layer thickness as we go along the plate, we see the tendency for this thickness to increase sharply at the beginning and then plateauing as we continue along the plate.